Welcome to this explainer. Whenever you walk across a massive suspension bridge or stand in the shadow of a towering skyscraper, do you ever wonder how we actually know, with absolute certainty, that the concrete isn't just going to crumble right beneath all that weight? Well, it doesn't happen by accident. Behind every major structure is this entire hidden world of unseen, high-stakes torture testing. So today, we're going to follow the thrilling, delicate, and ultimately destructive secret life of a concrete sample to see exactly what it takes to keep our built environment standing.
Okay, let's dive right into this. Here is the chronological blueprint of our concrete sample's life. We'll start with sampling fresh concrete, move to concrete age and strength, look at compressive strength cylinders, discuss preventing concrete failures, and finally, testing flexural strength.
Section 1. Sampling fresh concrete.
So this is the very first phase of our sample's life. And right off the bat, location is everything. Taking these samples exactly at the point of placement is always preferred over the point of delivery, because we want to test the exact material that's actually entering the structure. But getting that perfect sample, it's a total race against the clock. Honestly, you have to think of concrete less like a bucket of mud and more like a high-pressure baking competition. It's a precise chemical recipe, and the timer starts ticking immediately. Engineers have a strict 15-minute time limit to grab their sample and start their strength tests before the chemistry actually starts to set. It's literally a mad dash to capture the concrete while it's still in its perfectly plastic state.
Now, what's really interesting about this process is how we fix a bad batch. The rules are incredibly strict. If the concrete's consistency, which we call its slump, is off, there's a dramatic difference in the protocol. If the slump is too low, meaning it's way too stiff, you can add water, but only in highly controlled, specifically measured amounts that have to be officially recorded. But what if the slump is too high, like it's too soupy? You can't just sprinkle in a little dust to dry it out. No way. You actually have to add a full, unopened bag of cement from the exact same manufacturer just to soak up that excess water. It just goes to show how heavily regulated this seemingly simple mixture really is.
Section 2. Concrete age and strength.
Once we have that perfect sample, we transition right into the curing phase. This is where the material begins to mysteriously gain its structural power, and this brilliantly illustrates one of the absolute wildest facts about our built environment. Under favorable conditions, concrete actually cures and gains strength indefinitely. It never really stops. We do our early acceptance testing at 7 days, and the absolute gold standard for testing happens at 28 days. But get this, samples taken from old pavements show that concrete just keeps hardening for decades. The concrete sitting under a 25-year-old highway is actually significantly stronger today than it was when the road was just 1 to 3 years old.
Section 3. Compressive strength cylinders.
All right, now we prep for the iconic crushing test. This specifically measures how much pure downward weight the concrete can hold. And to make sure the test is totally fair, making a standard 100 by 200 millimeter testing cylinder requires a highly specific procedural rhythm. You don't just dump the concrete in. You have to place it into the mold in 2 equal layers. And for each layer, you literally plunge a steel hemispheric-nosed rod into the concrete exactly 25 times to consolidate it. Then, you lightly tap the sides of the mold with your hand or a mallet to force any trapped air bubbles up to the surface. It's a perfectly choreographed dance just to ensure there are absolutely no weak spots or voids hiding inside our sample.
And then comes the great irony of concrete. We're dealing with one of the toughest, most resilient materials on Earth, right? Yet for its first 24 hours, it has to be treated like a fragile newborn baby. These cylinders must be stored at a very comfortable 15 to 25 degrees Celsius. They have to be left utterly undisturbed, so no bumping, no vibrations whatsoever. Standard procedure even dictates using domed, perfectly white plastic molds specifically to deflect the heat of the sun. It's all about protecting our heavy-duty sample from sudden temperature shock and moisture loss.
Section 4. Preventing concrete failures.
So what actually happens when that precise recipe or that delicate handling gets compromised? Well, there are 8 fascinating and frankly catastrophic pitfalls that can completely doom a structure. We've got improper molding, which causes something called honeycombing, basically empty pockets in the rock. There's poor finishing on the top surface. Inadequate curing, where low temps permanently stunt the strength. Rough handling that creates these microscopic planes of weakness. Decreasing the cement content, using dirtier contaminated aggregates, which literally means the rocks won't bond with the paste. Adding excess water just because it makes it easier to pour. Or even decreased mix time, where a worn-out mixing blade leaves the sand and gravel completely uncoated. Just one single error from this list can drastically slash the lifespan of a multi-million-dollar project.
Section 5. Testing flexural strength. We have finally reached the climax.
This is the final, destructive chapter of our sample's life. We aren't crushing it this time, we're testing its tension through a snapping test. And we don't use small cylinders for this. Instead, we cast these large, rectangular concrete beams. The casting process here is incredibly intense. Because the surface area is so much larger, engineers have to rod the concrete an exhausting 65 times per layer. And once it sets, the curing goes to the extreme. The beams are completely submerged in tanks of saturated lime water. That ensures a perfectly controlled, moist environment right up until the very moment of testing.
So, the crucial point is, you have to handle these massive, heavy, awkwardly shaped stone beams with the utmost care when you pull them out of that lime water. In fact, the manual feels the need to emphatically, literally state, do not throw or drop at any time. It adds a bit of dramatic humor, for sure, but they are dead serious about it. Just a single drop could introduce a microfracture that completely ruins a month of perfectly controlled chemistry.
Let's move on and see how this builds up to the actual test. Right before the beam is placed into the braking machine, engineers pull out a set of calipers and a steel machinist's rule. They measure the exact center width and depth of that beam down to the nearest 0.5 millimeters. Every single microscopic fraction of a millimeter matters for the complex math that's about to happen.
Next up, the beam is hauled into this gritty, highly mechanical setup known as the third-point beam breaker. Honestly, it looks like an industrial guillotine. The beam has to be centered perfectly within the 4 tie rods, leaving exactly 25 millimeters of concrete protruding outside the bearing blocks. It's locked in, suspended, and entirely ready to be broken.
But how exactly do they apply the pressure? They don't just smash it with a giant hammer. They use this wildly complex recording chart system. Remember those ultra-precise millimeter measurements we just took? Well, those dictate whether the engineer loads spirals A, B, or C onto the machine's turning cam. Choosing the correct spiral ensures that the machine applies an exponentially increasing load at a flawless, agonizingly steady rate of between 125 and 175 psi every single minute.
And then, the test begins. The operator carefully traces the rotating spiral chart with a pen, visually tracking the force as the hydraulic piston bears down right on the center of the suspended beam. The pressure just builds and builds. The needle traces the line, climbing higher and higher, representing thousands of pounds of invisible force fighting against the chemical bonds of the concrete. This agonizing pressure continues, steadily climbing, until suddenly, with a violent, echoing crack, the concrete snaps. The test is over. The maximum tension threshold, its modulus of rupture, is permanently recorded, ultimately proving whether the bridge it represents is actually safe for you to drive on.
Our sample's life ends in pieces, but its sacrifice guarantees our safety. From that frantic 15-minute countdown in the back of the mixing truck, to decades of invisible hardening, to the agonizing pressure of the third-point beam breaker, the journey of this material is just an absolute marvel of modern engineering. So, the next time you step onto a sidewalk or drive over a massive overpass, take a moment to ask yourself, what unseen torture tests has the concrete beneath your feet right now survived?